Hello students, welcome to week 9 discussion class of Design of Photovoltaic System. This course is being taken by Professor L. Manan from Department of Electronic System Engineering, IISc Bangalore, and I am Ravi Kumar, a PMRF Research Scholar at IIT Bombay. So previously we have understood what is a photovoltaic cell is. We have seen PV module. So from PV cell we have PV module. Then we have also understood the IV characteristics. And from this IV characteristics, we have understood what is this MPP, that is the maximum power point in this curve. This is a point at which maximum power can be drawn, and this MPP, that is the maximum power point, can be obtained by using MPPT trackers. And then after that, we have seen the integration of battery with solar PV, and in this particular class today, we will understand what is this Peltier module is, how it works, and what are the applications of this Peltier module. So now then we will solve few problems based on this Peltier systems. So Peltier means we have different metals, we can say dissimilar materials, and we have junctions. So at the junction there are temperature effects. So if current flows from one junction to another, so one junction become hot and another become cold. So this is the basic principle of this Peltier system. And we don't have this dissimilar material nowadays, but in place of this we have this PN junction, that is a semiconductor materials in the form of an array. So it's like NP. So this is an array, and then we have copper contacts. So these junctions also have the same effect as the dissimilar metal have. So this is also known as Peltier effect. And so we have large number of these junctions in series, so the area of these junctions will increase. So we have large area of this hot and cold surfaces. So also we have, if we purchase a Peltier system, we have few data sheets. So this is a Peltier system. This is the current which goes in. This is the voltage which required to this Peltier system. This is the voltage source. This is the temperature of hot side. This is the temperature of colder side. And then we have this maximum and minimum hot temperature. What is the Qmax? This QC, that can be obtained or can be taken from this cooler to hotter side. Then we have this delta T max. What is the delta T max? Can be obtained. Then we have this maximum current of Peltier system. Then we have voltage across this Peltier system, and then we have module resistance, which is given in the unit of ohms. And other than that, we have two characteristics as well, thermo and electric. So it is like delta T versus QC. So it means if the temperature difference between hot and cold junction increases, so the performance QC is the capacity to take heat from cold junction to hot junction, it decreases. So with increase in delta T, our QC, that is the capacity to take the heat from colder to hotter junction, decreases. And also then we have a characteristic that is electric in nature. So it is delta T versus voltage. It means as the delta T increases, our voltage requirement also increases. So with delta T increase, voltage increases. Somehow I was not able to record this video. Okay. So yes, we have this Peltier based system. We have this Peltier module. We have this PV module, and using this DC-DC converter, we connect this PV module with this Peltier system, and it becomes an entire photovoltaic based system. Okay. So where we are going to use this Peltier based cooling system? So let us understand this way. We have an IC, and in this IC we need to that dissipate like large amount of heat, and with the heat dissipation the efficiency of this IC drops. So what we need to do, we need to remove that heat from the IC so that it can work without any hurdles, without losing any efficiency loss. So first option what we have an IC like this. We have an atmosphere. The heat which is being generated here will go to the atmosphere directly. And if this condition, we just use these thermal equations and we just calculate what is the temperature that can be possible here minimum. So it will be around 240 degrees Celsius. That is the huge temperature. It is very high. Okay. So other than that, what we can do? We can have some automatic cooling. How? Using some fins or using some another material. Usually what we have, like over the NIC, we have this aluminum fins. So those increases the area and helps in dissipating the heat. So similarly, we can have this IC, and we can have these fins, and we can have an atmosphere. And in this condition, if we calculate the temperature which is the possible here, Tj minimum temperature, it is around 72 degree Celsius. So it is a large drop from 240 degree Celsius to 72, and it is without using the Peltier system. And if we are using Peltier system, it can be much lower as compared to the 72 as well. We can reach around 25 to 30 temperature. But how we can do this? We can have this we can have this Peltier system in between these fins. This is the IC. Then we also can have a fan. It will give the force convection, and due to this force convection, the heat dissipation from these fins will be more, and in this way we can drop this Tj much lower, and this Peltier system will work on this solar PV system. So this is all about the Peltier based cooling systems. Wait a minute. Yes. So this is the Peltier based cooling system. Now before going to this actual questions, we need to understand few concepts related to this thermal aspects. So we know this thermal energy, or like how many ways and heat can dissipate and heat can flow. Do you know? If you know, you can write in the chat box. How many ways heat can travel, heat can dissipate? Do you know conduction? Do you know convection, radiation, and mass transport? Yes, so these are the ways, like one is the conduction, then we have convection, then we have radiation, then we have mass transport. So these are the four ways by which this heat removal can take place. And in this particular Peltier based system, we can use one or four or all as a combination. And then what are the thermal relationship that are also important? How this heat dissipation is related to the temperature difference and thermal resistance. And it is written in the resistance form. It is also can be written in the thermal resistivity form. Resistivity means it is per unit area. And also we can get this thermal coefficient form as well. It is 1 upon R now. So this is all about this thermal aspect, thermal relationship and the Peltier based PV system. Now we will solve few questions. So first question is here. As shown in figure, a battery that is 30 volt is interfaced by using an electronic converter with a Peltier module. Find the maximum duty cycle at which the switch can operate for the safe operation of the Peltier module at 50 degrees Celsius. So this is our, you can say this is our Peltier module. This is our battery and this is our DC-DC converter. The question is asking, because in this DC converter we have a particular value of D, that is a duty cycle. This duty cycle is helpful in controlling the voltage. So the question is asking that what is the maximum duty cycle which can operate this Peltier module safely at 50 degrees Celsius. And these are the data sheets. This is the data sheet of the Peltier PV system and these are the options. How can you get this? Any idea? Solve this if you know. If you don't know, let me know. I will help you. Okay, you don't know. See, there are two voltages. If you can see, if one voltage will be here, one voltage is given here. What this DC-DC converter do? It changes the voltage, current, we can say, or resistance across two different terminals. So here in this case, we know this voltage. This voltage you can also get from the data sheet. And this relation between this V in and V PM, relation between V in and V PM Peltier module can be obtained from DC-DC converter relations. So before that, what you need to do? First, you need to understand which DC-DC converter is being used here. Which DC-DC converter is this? You can write in the chat box. If you don't know, it's okay. If you know, buck. Yes, Mohan, it is buck. Okay. So for this buck converter, what is the relationship between this V input and this V PM? If you know it, let me know. If you don't know, it's okay. Multiply V. Yes. It is like V input equals to D into VPM. And so D will be into D. Sorry, this D will be here. So D will be D PM divided by D V input. And this question is asking at 50 degrees Celsius. So this 50 degrees Celsius voltage will be 16.4. So from this data sheet we are getting 16.4 divided by 30. How much we are getting? Yes, I have also given here. This is the buck and this is boost. So it is buck here, and this is the relationship for the buck multiply by D, and based on this we are having like D equals to 16.4 divided by 30. How much you are getting? Just divide it. Divide 16.4 divided by 30. 16.4 divided by 30. How much you are getting? Okay, I'll do it. It's okay if you don't want to do it. Mine is coming 0.54. So 0.54 should be the answer here. Yes, this is correct. 0.54 is the answer. Let's move to the next question, which says in the same previous question there is a resistance inserted here. That is the RSE. This is the resistance have been inserted between this Peltier module and this DC-DC converter to limit the current to the module in the figure. Duty cycle is given. So D is given like this. D is equals to 0.7. So 0.7 is the D. Find the value of resistance required to provide a safe operation. Means you need to find the value of this RS. And these are the options. Can you do it? Can you do it? No? Yes? Okay, we will do it step by step. So, one voltage is this, V input. One voltage is this, VC. If D is given already, can we calculate VC using this relation? Multiply with D. So 0.7 into 30. How much it is coming? 21 volt. It is VC, right? Yes, no. I'm audible or yes, no? Okay. Okay, Vikas, thanks. So now this is 21 volt. Now we will reduce the circuit like this. So now we will say 20 volt battery. This is our Peltier module, and this is our RS. This is the value which we need to obtain. Okay. So to obtain this RSE, what we require? The relation of Ohm's law say R equals to V by I. What is the voltage across this resistance? Voltage across this resistance? Can you get this voltage of resistance from this Peltier module datasheet? What is the current flowing through this I? Twenty-one is the voltage which is across this resistance and Peltier module. It is across the both. Particularly across this, it should be VRSE. I am writing VRSE. It should be 21 minus voltage across Peltier module divided by current. So not if just voltage, then it should be like this only. Yes, Mohan, you are right. So see, we get this voltage across this resistance as 21 minus 16.4, that is the maximum which is allowed, divided by I maximum we can also take from here because current in this circuit will remain same. This is the current I, and this I can be taken from this data sheet which is 6.4. So it will be around, solve it, 21 minus 16.4 divided by 6.4. I'm getting 0.7. Whatever you are getting, let me know. 0.7. So it is 0.7 ohms. Here D is the right answer. We also go to the D as the right answer. Okay, we will move to the next question. So in this question, you don't require any help. So the admittance of a polished aluminum is, you have the options A, B, C, D. It may be multiple choice question as well. Admittance of a polished aluminum. Admittance is the property of a material related to the radiation emission capacity. How radiation it can emit. What do you think? The admittance of this polished aluminum, what do you think? Okay, now tell me the answer. Now answer is in front of you. You just need to tell me. At least now you can say something A, B, C, or D. Emittance value already given. The options which are there already mentioned in this table. What is left? Okay. Rasmi said A, B, and C. How B? The B option says more than rough surface aluminum. Rough surface aluminum is 0.18 and polished aluminum is 0.09. So which one is more? It is less than. The polished aluminum is less than this rough surface. And this option is saying more than. So I think option B is not right. What do you think? Okay, Rasmi said A, C, and D. A, C, and D. Yes. A you can see here less than C. The value here I am writing 0.095. The value of this 0.8. The value of wood, the value of 0.18, 0.9, copper 0.07. So less than this anodized aluminum, yes, it is less. Yes, first is right. More than the rough surface, no. Less than the wood, yes. More than the polished surface, yes. So we have this A, C, and D are the correct options. Great. Let's move to the next question. Which says in a convective Peltier cooling system. Convective means it is a mode of thermal dissipation. An air blower is used. If air blower is used, then it is forced convection over the hot surface of the square shaped Peltier element. The side length is 4.5 cm. If Reynolds number is 7500, then find the air speed coming from the blower. This is the kinematic viscosity is given of the air. This 1.8 into 10 to the power minus 5 meter per square per second. And these are the options. If you know the formula, apply it. If you don't know the formula, let me know. If you require the formula, let me know. And if you know the formula, let me know the answer. Yes. Formula should have a relation between this Reynolds number, kinematic viscosity, this blower speed, and characteristics length. A formula which is having all these components will be used. Okay, I think you don't know the formula. I am writing here. So this is the formula. This is a relationship between this Reynolds number, speed, and kinematic viscosity. Now apply this formula and let me know the value of this u. This mu is the
Sir,
yes,
sir, I have a doubt in previous question.
yes,
Yeah. Sir, can you go to that, please?
yes,
No, not previous to this. Previous to this.
yes.
Sir, why we have here the temperature is mentioned, not mentioned. Okay, but you considered of 50 degrees centigrade. So how it is done, sir? Getting my doubt, sir.
Yes, yes.
So here we have directly taken 16.4 as the Vmax value and Imax value as 6.4.
Okay,
Why not 14.4 as Vmax? Imax is same, but why not 14.4 since here the temperature is not mentioned?
okay.
So
So let's say if you will take this lower limit 14.4, then your resistance will be high. And if this resistance will be high, then it will limit more current. If you will give this here 14.4, how much value you will get? This R,
yes, sir, it will be more
it will be
because
more.
the difference will be more. Yes.
Yes. And if this resistance will be more, and if I equals to V by R, so this I will drop.
Okay, so if like this data sheet is given, we should consider
Maximum limit.
maximum value only
Yes,
if the temperature is not mentioned.
yes.
Okay, thank you, sir.
And even like Mohan also said, right, with respect to question 1, it is what saying 15 degrees Celsius. That is also right. Even if it is not given, then solve it for the higher temperature only.
Okay, sir.
Yes. So we were here. So use this formula and calculate this speed. Just put the value and solve it. Mohan, Rasmi, how much you are getting this? Like value of u. See, from this u will be Reynolds number into mu divided by x. What is the Reynolds number here? 75000 into what is this kinematic viscosity? 1.8 into 10 to the power minus 5 meter square per second divided by how much it is. This is the characteristic length. So it is 4.5 centimeter converted into meter. Calculate it. Do the calculation at least. Okay, I'll do it if you don't want to do it. 75 B. Ruchi said B. Okay, let me check. Into 1.8 divided by 1.5. Yes, it is 3. Exactly 3. Yes, Rajnikant, it is 3 meter per second. So we are getting B. Let's move to the next question, which says a solid slab shown in figure has dimensions follow: length, width, and height. Cold side temperature is given 293 Kelvin. Hot side temperature is given 307 Kelvin. For a difference between Q and Q2, that is the heat flowing, it is 25 watt. Calculate the thermal conductivity of the slab, and these are the options. Simplest question, thermal conductivity calculation. Do you require a formula? What all things we have given? We have given T1, that is 293, T2, that is 307. The heat flowing, it is given 25 volt. This L is given 5 centimeter. This H is given 3.5 centimeter, and this width is given 1.5 centimeter. These are the things already given. And for thermal conductivity, we know this is the relation. Q given, K is the thermal conductivity which need to calculate. A, it is the area. T2 minus T1 is the temperature already given. D is the width already given. Calculate this. And even in these terms you can have this. Let me check if we are getting the answer. let's check the unit of this formula if it is right. So we have K, unit of this Q will be watt, this will be meter, then A will be meter square, and it will be Kelvin. So it is watt per Kelvin per meter. It is right. Okay, you can solve it now. 15.3. I'm also getting something like this. There may be some difference in the values, maybe. Delta T is 14 into 25. Q D what you guys are getting? I am also getting something like this. Let me check once again. 25 into 0.015 divided by 14 divided by 0.05 divided by. Yes, I think there may be some error in these options. So I'm getting this 15.3 value of K using this formula only directly. Yes. So answer will be 15.3 and unit will be watt per Kelvin per meter. Okay, let's move to the next question. It said, what is the maximum amount of heat in kilowatts that a 2-meter wide anodized aluminum block radiator measuring 10 meters in length, initially at 80 degrees Celsius, can dissipate from top side of the system through radiative heat transfer as the ambient temperature is 40. Assume the admittance of the anode is 0.8, and these are the options. See, first understand the question. The question says we have a surface like this. This is the surface. The temperature is 80 degrees Celsius. Atmosphere temperature is 40 degrees Celsius, and it is the radiation which are coming out, and it is given like 80, 10 meter and 2 meter. These are the dimensions, and the emittance is given 0.8. These all the informations are given here. You need to calculate the Q, that is from radiation. So here you can directly use the Stephen-Boltzmann law as well. Using this Stephen-Boltzmann law, you can calculate this value of Q. Do you know the formula for this Stephen-Boltzmann law? Yes, no? Okay, so this is the formula, and these are the meaning of these symbols. This Q is amount of heat transfer. This epsilon is surface emissivity. Yeah, these are the like few formulas which you might need to remember. Actually, I don't have any idea about the final exam, how it will be, so I cannot say. But yes, few formulas you must remember. Like Stephen-Boltzmann is very simple to remember this. And if there is some constant, that should be given in the question also. So this sigma is Stephen-Boltzmann constant, value is given here. A is the area, TS is the surface temperature, TL5, A is the ambient temperature. Just put the values and find the answer. You will give it like 0.8 into 5.67 into 10 raised to the minus 8 into 2 into 10, and then multiply. I am writing here 273 plus 80 raised to the power 4 minus 273 plus 40 to the power 4. Do this. Make sure you convert all the temperature which is given in degree Celsius into Kelvin. How much you are getting? I will solve this here. So I am getting 0.8 into, so I'll start from there, 273 plus 50, 353 raised to the power 4 minus 273 plus 40 raised to the power 4 into 2 into 10 into 5.67 into 10 raised to the power minus 8 into 0.8. Okay, I'm getting 5379.22 watt. So converted to kilowatt, 5.3438 kilowatt, and we can write it as well 5.4 kilowatt. So answer is B. So B is the correct answer here. Yes, Rajnikant, you are also right, 5.4 kilowatt. Let's move to the next question. This question is also like similar to the previous one. The same formula will be applied. Just understand what this question is saying. It is saying determine the rate of radiative heat transfer in a strip of copper. Rate of heat transfer means what? What only? A strip of copper. So this one is copper, this one is ammonium. The length is given 5 meter, 10 meter respectively. So it is our 10 meter and it is 5 meter. With the breadth is given to 2 meter. The shielding factor, this is the extra term here. Shielding factor is 0.8. So we can say phi is given 0.8. Given an initial temperature 80 degree, temperature is given 80 degree for both, and a surrounding temperature 30 degree. So you can assume 30 degree Celsius here, 30 degree Celsius here, and 80 degree Celsius here, and 80 degree Celsius here. Consider the radiative surface as per the arrow direction. So this is the radiative surface direction given in the arrow. And emittance is given for this polished aluminum as well as for polished copper as 0.07 and 0.095. And these are the options. Options, okay. Options is like 108, 158, 208, and 258. These are the options. So what you need to do, the same formula which we applied before, use this surface plus use this surface and add them. Add the value which you are getting from here, Q for copper, Q for aluminum, and total Q will be Q for copper plus Q for aluminum. And here this particular phi term is important. So whatever you are getting from the radiation, you need to multiply with 1 minus phi. The shielding factor and limiting factor are same. No. Shielding factor and emittance factor are different. See, this is the formula we already have for this radiation, and this is the value of Stephen Boltzmann constant. Then with the shielding factor, this formula will be multiplied by this phi will be the shielding factor. One more term will be there. So using this formula, first let me know what is the value of copper, QC. Shielding means it is like having an hurdle to the radiation. So 0.8 radiation is not going out. You can say 80% radiation is limiting there, being shielded. So only 20% radiation will be available. So first calculate this Q for copper. Put the value of copper. Okay, what is the temperature in Kelvin? We can say 273 plus 80. It is 353 in Kelvin, and it is 30, right? 273 plus 30, 303. So first calculate for QC, then calculate for QA. How much you are getting for QC? Use this formula. 108. 108. Let me check. We are getting 108. 353. It is for QC, Rajnikant. No, I am getting 56. I am getting for copper 56 watt. There might be some mistake in the calculation. I think you have like may have like let me check. That is the problem. Maybe you have like taken the emittance wrong or like something else. Figure it out, or maybe the area. Area may be the one term because you are getting a difference of 2. Okay, so what about the aluminium? See, top we already got. Now calculate the bottom part. I'll calculate for the bottom part. I have got for the bottom part as well. It is coming 1. What is the value? 152. Now let's sum it. How much it is coming? No, it is not. It is not considering the like if it is R in the same direction or in the opposite direction. Let's take the heat is coming from the system to the atmosphere, and if it is coming to the atmosphere from the system, then we will add them. We are just taking the top surface and the bottom surface. Other things we are ignoring, and we are saying the heat is coming from the system to the atmosphere, So from the upper surface as well, it is coming to the atmosphere. From the bottom surface as well, it is coming from the to the atmosphere. That's why we will add both the heat transfer. Let's say if you have a circle or sphere and heat is coming out, so you will not subtract this heat from this heat. Then it will be zero, but there will be some radiation from this sphere. So we will add all the heat dissipation. So the summation will be 208 volt. So answer here is C. Okay, Maman. I hope you understood this. Because in case of sphere, it will be 0 if we will subtract. But it won't be 0. Okay, let's move to the next question, which says an inverter for driving an automotive motor is made with a forced mass cooling using water. So this is another type of heat transfer, that is the mass transfer. So here mass is water, which is used as a forced mass cooling system. It is like 50 watt of the rate at the heat transfer need to be extracted. So that is the Q, what need to be extracted. Consider a mass flow. Mass flow is given of this liquid or water 10 gram per second, and the specific heat capacity is given 4.18. Calculate the thermal resistance in Kelvin for what? For mass flow rate in cooling system of inverter. And these are the options. Here we have important term like dm by dt, that is the mass flow. It is equals to 10 gram per second. Then what all is given? Specific heat capacity, 4.184 joule per gram per Kelvin. And then what is given? The heat transfer. Q is already given 51. But we don't require this Q. We can solve it without Q as well. We have a simple formula for this. See, this is the formula. Directly for the thermal resistance, it is saying R will be equals to 1 divided by dm by dt into specific heat. Calculate it. 1 divided by 10 gram per second into 4.184 joule per gram per Kelvin. How much you are getting? It is 1. So we can cancel this gram with the gram. D 0.024. So 0.024. And this joule per second will be watt, and this is the Kelvin. It will go up, so it will be Kelvin per watt. So D is the right answer. Yes. Let's move to the next question, which says calculate the thermal resistance of the heat sink placed at the hot side. Which is the hot side? where the cold junction and the hot junction temperature of the peltier elements are 80 degree and 100 degree. So this is our peltier system. It is like 100 here, 80 here. The rate of heat flow through the peltier element in the heat sinks is 50 watt. It is the heat flow is given. The surrounding ambient temperature is 30 degree. So ambient is here 30 degree. Assume the thermal resistance between the cold junction and the hot junction, which is already given 0.75. And 0.5. So you need to find out this thermal resistance of this heat sink. Simple question, very simple one. If you just consider this entire circuit as an electrical circuit, you will be able to solve it within few minutes. These are the options. In our electrical circuit, temperature corresponding to voltage and this heat transfer corresponding to current, and this thermal resistance and resistance are same. See, thermal and R electrical are same. So using this relation between this thermal and electrical motors, you can calculate this thermal resistance of the heat sink. Let's say this is the entire resistance R, T, R thermal, from this to this. So what should be the value of this RT? If it is electrical, let's say it is electrical, and this is V1, this is V2, and this is R. So this R will be R equals to V by I. So it will be V1 minus V2 potential difference divided by current. And I am saying V corresponds to this temperature. So it will be TC minus TA divided by this current corresponds to this heat transfer, that is Q. It is Q. So it will be 80 minus 30 divided by 15. So this is our entire RT. And what is this RT? RT is a combination of RCH plus RHS plus RSA equals to RT. RCH is given 0.75 plus RHS given 0.5 plus RSA we need to calculate. RT is 80 minus 30 divided by 50. What is RSA is coming? calculate this. So simple, just let me know the answer. Anyone solving this? Very simple, do it. 80 minus B to Rajnikant said B, okay. 80 minus 30 divided by 15 minus 0.75 minus 0.5, 2.08. And 2.0 is corresponding to B, so B is the right answer. So simple. Let's move to the next and last question. It says, in a Peltier device, the energy extracted from the cold junction is 25 watt. The electrical energy supplied is 20 watt. Then what is the heat energy transferred to the heat junction? And these are the options. So simple, the simplest question. See, it is given this heat as 25 watt, this energy as 20 watt. Yes, mom, tell me. Okay, Rajani answered 5 watt. We will see. We will look into it. Go on, you can write what doubt you have. Yes. Yes, 80, it is cold, it is hot. Yes. Why we are subtracting from 80, not from 100? Because we are taking this entire R, thermal resistance of this entire circuit. And cold junction is at this end, not at this end. If this is the thermal end, just understand the configuration. TC is the extreme left and TA is the extreme left. Because heat is extracting from here, it is the direction of heat flow, like from here to here. This is the direction of heat flow. Heat dissipate from 100 to 30. Yes, definitely it will flow. But see, from this configuration, let's see. See, just understand one thing. Heat is also coming from this cold junction because we are forcing heat to come from this cold junction. That's why it is being colder. From 100 to 30, it will be a automatic heat dissipation. It does not require any kind of source or energy, or like we can say the heat motor, heat pump. Exactly, we say heat pump. So we don't require heat pump. We require heat pump in one where that heat we need to take from cold junction to the hotter junction. Then we require this heat pump. So in this case also, this is the colder junction, this is the hotter junction. If you are saying we will like subtract this from 100, then we can only get this particular resistance, the combination of this RHS and RSA only. Take it as an electrical circuit. Yes. Okay, we were at this question. So like Rajnikant said, 5 volt. Okay. Understand the direction of arrows. "20 volt coming in, 25 volt also coming in, and all heat is going to the outer part. So how much will be the heat? 45. Yes. Correct answer is C only. So we are done for today. This is all about the today. We will meet next Friday at 6 p.m. How? Mohan, here we are just see if we are giving some heat. Yes, I am explaining you. Wait. Which option is that? This one. See, very easy to understand here. This heat, this is the 20 watt which is being injected to this part, and this is the 25 watt which is coming from this colder part. See, continuously if 20 watt will be coming here, so there will be some source which is taking this heat. This is some heat convection or heat transfer is taking place to this cold junction as well. So the amount of heat which are giving to this Peltier system 20 watt, it is continuously being taken out by some other fluid. Like alternatively, we can understand this. This is also an heat generating unit. This is also heat we are extracting from this cold junction. Then we will add them. But in real condition, the exact scenario is that this colder part, if continuously 25 watt is being extracted here, so some fluid is there or some kind of heat generation is here, which is making this Peltier system to work continuously. And this particular heat transfer is taken to this particular unit. Let us understand this way. We have an IC here. Let's say IC. And we are keeping it at 25. We are taking 25 watt heat continuously. So here in this particular IC, some heat being dissipated with time. So that heat dissipation here will be equal to energy given to Peltier system. So it is like not directly but indirectly, this heat which is generating from the IC is forcing our Peltier system to extract this 25 watt continuously. That's why we are adding both 25 and 20. Because this colder part, what do you think? This 25 watt extraction will be continuous when there is some source towards the colder junction. If colder junction is given, colder junction is not having any source, then this 25 watt will be infinite. So can it reach to the minus infinite temperature? No, it won't. Or we can say the 0 Kelvin temperature. No, it won't. But 25 watt extraction can take place only if there is some heat dissipation towards this colder junction part, and the heat taken or heat dissipation at this colder junction will be equal to the heat or energy taken by the Peltier system. And that's why we are saying 20 plus 25 will be equals to 45. Yes. C answer here. Yes. Okay, bye everyone. Take care. We will meet in the next class next Friday, 6 p.m.